ফোর্স, স্ট্রেস, স্ট্রেন, ডিসপ্লেসমেন্ট যে রিলেশন গুলো এটা নিয়ে জাস্ট ডিসকাশন করা হয়েছিল।
ওকে। তো the thing is আমরা ফাইনাইট এলিমেন্ট মেথডে দেখেছি that we need a strong form which basically consists of a set of governing differential equations and boundary conditions, and from which we would go for the v statement, and likewise we will solve our I mean, first we propose our problem in variational formulation, and then we would discretize the geometry, and the node and the mesh, all those formulations would come, and then shape functions and everything would come, and from that we would have the finite element model, and finally we will solve it. So basically there are 4 stages to it. So we have already figured out the first one, which is to get the strong form. Okay, and I think we have done enough discussion on the strong form, so we can directly write those equations. And today we should at least be in a position to get the v statement. Okay, so I'm just writing a set of equations. Still dwelling in the domain of small strain. That's why it doesn't matter about which configuration are we taking the divergence. It's a divergence of a matrix, which is a second order tensor. So what do we get? We get a vector, and this is our linear momentum balance. But then we can get rid of this quantity when we are in equilibrium. Okay, so please note this acceleration that we are talking about. This is one way to write it. The second way to write it as del sigma ij del xj, and this is in Einsteinian notation. And if that is not really clear to you, so basically we are looking at a vector set of equations. So basically these are 3 equations of motion or 3 equations of equilibrium, depending on whatever the right hand side is. So it's a vector equation, 3 equations, 3 rows. So I'm just writing for the for all I in 1, 2, and 3 equals rho uy double dot, of course, but then in equilibrium this quantity goes to 0. Now
Yes, this part was
the
wrong.
Einstein,
You explained
sorry.
it.
So this
You
is,
explained the Einsteinian convention.
yeah. So it is this is known as indicial notation. So basically, you are talking about only one component of that vector. So a vector equation can be thought of a vector in itself. Okay. So the right hand side of this vector is 0. Okay. So this one is not a 0 vector. This is a 0 scalar. So the right hand side of this equation is 0. So the left hand side is essentially a vector comprising of partial derivatives and other quantities. Now the thing is, this quantity right here is actually not a single term. It's a summation of 3 terms. Basically, in Einsteinian notation, every time you have repetition of any given index, okay, so that is essentially you're representing a summation. So this is actually a summation over j going from 1 to 3. So what do we know? That you had a matrix sigma, the Cauchy stress, whose individual components were ij, where I would indicate the direction in which the traction is acting, and j would indicate the plane on the normal, the direction to which the plane is normal to. So if you think about a unit, not unit, but a differential element anywhere within the material, uh, okay. So in that if you choose any given plane, that would be normal to the direction j. Okay, so you can refer to the x direction being 1 or e1, this one being e2, and this one being e3. So you can consider uh, a plane which is normal to one of the three directions, three Cartesian directions, and that would be represented with j. And that on each plane, each of those plane, there would be three components of the traction, and each component would be referred to with I, where I represents the direction in which the component of the traction that is acting. Okay, we have discussed in length. We have also, shown detailed diagrams for that. So at this point, it should be clear. Now imagine you had this entire row where j is changing. So I changes with row and j changes with column. Okay, so if you take a single row for any given I, imagine this entire row of the sigma matrix. For example, sigma 1 1, sigma 1 2, sigma 1 3. And then what you do is you take the derivative of del sigma 1 1. So basically, if you say that that the coordinate or the configuration be given by the components of the vector x1, component of the vector x, which are x1, x2, and x3. So then this summation right here is essentially del sigma 1 2 del x2 plus del sigma 1 3 del x3. Okay, and so basically what we are seeing here, that you take a given row and essentially take the divergence of that quantity. So treat this row as a vector and take the divergence of that, and that scalar is the ith component. Take the ith row, take the divergence of that row. Ith row is a vector, row vector, and then you take divergence of that vector, and essentially that is the ith component of the divergence of that given matrix. Is it clear up to this part?
Sir, just noting it down. First, we take a single row, and then we take the divergence of that vector, the row vector which we are getting, which we are picking, and
Yeah,
then
that is
we are
the
getting
ith component of the divergence of the stress tensor.
that is the ith component of the divergence of the stress tensor.
Okay.
Okay. Yes, sir.
Okay. And let's now talk about the boundary conditions. So u is given to you as u bar in gamma u. Okay. So basically, you know the value of u in gamma u, and t may be given as t bar in gamma t, which basically means that sigma n in gamma t, sigma times the normal in gamma t, usual Cauchy equation, equals t bar. Okay, so this is actually the definition part. So these two are essentially the same, but then you are saying that I know the value of the traction in gamma t. Okay, that's what this means. That's how you problem. That's how you pose a problem in structure engineering. Okay, is it clear?
No, sir. The last line was not clear. That sigma n is equals to t in fraction boundary
See,
condition.
sigma n equals t. So that is the
Mm-hmm.
very definition of traction. That, I mean, it's not a the very definition, or rather, you can call it the very definition. The thing is, we actually got the expression of sigma through this kind of an exercise, and then we define the matrix that would relate to the traction through the normal. Okay,
Normal.
as the
Yeah.
Cauchy stress tensor. So the very definition of Cauchy stress tensor is this equation right there, Cauchy's
Yeah.
equation.
Yes, sir. Yes, sir. Yes, sir.
And that traction happens to be known in gamma t. Imagine the cantilever beam,
Okay.
the free end,
Hmm.
whether you apply a concentrated force or a concentrated moment or nothing. Okay,
Hmm.
whatever the case may be, but you know that. Okay, So you know that information about the free end. So in gamma t, you know the value of the traction.
Okay.
Now,
The
what is the
traction
equivalent?
here, I'm basically referring to the amount, what change, the meaning what type of forces I am putting into the
No, see, the
mechanism.
meaning of these two equations are that these two are known to you. Okay. For
Okay.
example, in the cantilever beam, the fixed side, you'd mention that the displacement and the rotations are zero.
Yeah.
So you know those values, and those
Hmm.
values happen to be zero. Okay. So that is that. If you classify the u vector at any
Hmm.
given location as w theta, which we did with beam elements, so
Hmm.
that u bar for you should be 0 0, the vector of
Zero zero. Yeah.
constants.
Yes. Yes.
That's all I'm saying. Okay.
Okay, I got it. Yeah.
Okay. Similarly, this t bar is also a the vector of constants that you know, or not. It doesn't have to be a constant. It could be a function of the coordinate along the boundary. Okay.
Okay.
For example, uh, mm, if you have this geometry, and
Hmm.
you applied some sort of distributed load which is changing linearly. It could be changing any other way, but the thing is,
Hmm.
it's only at the boundary or in gamma t, and it changes with the coordinate or the locations on the boundary. Okay, it has nothing to do with coordinates inside the volume. It only depends on the coordinate in the on the boundary, because it is
Boundary.
being applied at
Boundary.
the boundary. Okay,
Yeah.
so that's it. uh,
Okay.
okay, now at this
Yes.
point we would also need to talk about something called constitutive relations. Basically, on one side of the constitutive relation is stress tensor, the other side is strain, and the functional relationship between the two is the constitutive relation. The simplest that we have seen so far is this one for uniaxial problems. Uniaxial uh, uniaxial heat transfer problem, we have seen that Q heat flux is K times dt dx. Okay. Now, why there is a derivative of T? If you really think about it, it's actually a problem posed in uh, stress and displacement. So it is actually du dx, if you really think about it. Okay. So essentially, the 1D heat transfer problem and 1D, structural problem, they are essentially the, same problem.
Yes, sir. Yes. They're basically derivating about the direction in which we are taking the change.
Yes. Okay. That being said, now let's look at constitutive relations. Now, there are so many constitutive relations. I mean, the constitutive relations actually depend on how we model real life objects. Okay, uh, in engineering problems. For instance, this is how a metal behaves, a ductile one, and at any point, if you did an unload, it would follow a path which is more or less parallel to the initial linear portion. Now, this initial linear portion, okay, which is more or less the elastic portion as well, okay, where the Hooke's law is valid, that is, to be frank, of the order of this much of strain. And this is how rubber like materials behave. Not to scale. And when you unload, it more or less follows its loading path. It could be doing something like this. Let's say you unload it from here. It could be doing something like this, but more or less it follows its loading path. Now, what is to do with loading path? Well, if the loading and the unloading curves are exactly the same, then the material is perfectly elastic. Okay. Why so? It means whatever energy that you put in the form of work done to the material per unit volume, and that's what the stress strain relation is actually, force per unit area and displacement per unit length. And when you do this integration, that essentially per unit volume work done. Okay. So whatever energy you had put, you can get it back when the loading and the unloading curve are the same. There are pseudo elasticities, namely viscoelasticity, and there is super elasticity. There is an alloy called nitinol, which actually goes through phase transformation from austenite to martensite in the process. Viscoelasticity typically observed in glass. This is typically observed in rubber-like materials, and this behavior is classified as hyperelasticity. So for rubber, this strain, okay, the extent of strain up to which it can more or less behave like a elastic material, although non-linear, that extent could be, greater than 100%. Okay, or I mean, typically
100 E, 100 times E.
no,
Excellent.
1 to 10. I mean, you can imagine a strain of 1, which means it can
Yeah.
elongate. Uh, I mean, think of a rubber
So
band.
double itself.
How
Double
much can it
itself.
elongate? Yeah, so it can,
Two times the speed.
uh, yeah, it can elongate up to 1000% and still be elastic. Okay,
Okay.
not all rubber materials, not
No.
always, but just an comparison of the
Okay.
order of magnitude. Okay, here we are talking about 10, and here we are talking about 10 to the power minus 3. There are 4 orders of magnitude of difference. Okay, now I'll come to my point, but I need to discuss a few things before that. So one is viscoelasticity and hyperelasticity, which would typically look something like this. When loading and when unloading, possibly something like this. Can you tell me why am I calling it pseudo elasticity?
Sir, because it's returning to its original position, but not along the same path.
Yes. And what does that mean? While loading, you can imagine the area under the curve
Hmm.
is how much energy per unit volume that you are putting into it. Okay.
Hmm.
Of which viscoelasticity is also rate dependent.
Sir, rate dependent. I did not get
That
that
means the
point.
strain rate matters. Okay. If the strain rate is quite high, it would behave in a certain way. If the strain rate is slow, gradual, it would behave in a different way.
Okay.
And such behavior is also seen in superelasticity. And it's at times it is very difficult to distinguish between superelasticity and hyperelasticity. And this is the energy that you got out of the system when you were unloaded. So if you hung a weight while you were unloading, the work done on that weight below the tensile specimen would be would be only this much at best. So you see the difference between the two area. That is the amount of energy lost, okay, in the process, in the cycle. So the idea here is that our undergrad, or rather the school level definition of elasticity, where we would simply memorize or remember by heart that elasticity is a property by virtue of which the material regains its original configuration after the load is removed. But that's only the partial definition of elasticity. In order to be true elasticity, it must follow its loading curve while unloading. Then, of course, when the entire load is removed, it will regain its configuration, because it has to come back to origin, which is 0 0, and zero strain would mean original configuration. Of course, this part beyond the elastic limit for a metal is plastic, and hence, when you unload, a portion of the strain remains, and that portion is the plastic strain. Now, given all of this, why did
So
I
there is
mention?
one thing I need to clarify. Let's say we are using a super elastic material,
Yes.
like you have drawn here. So some residual force is this force being lost? Is this work or the work which we are doing in stretching it and then releasing it? Is that work
Mhm.
being lost or it is being stored in the system? Like in the rubber band, let's say, if we are talking about a rubber band.
Okay. Uh, in rubber band, you can see the loading and unloading curve are really close, so you can see more or less the energy is conserved. Okay, and the
Hmm.
mechanical energy form of the energy is conserved. And the answer is answer to that other question of yours. That is the pretty low hanging fruit. What happens to any form of energy, mechanical energy that is being lost? What happens to that?
It's form of heat, in the form of heat
Yeah,
or
yeah, in the form of it. That's it.
okay.
Okay, in the form of it. That's how it works in plasticity. So even in plasticity, when you completely remove the load, okay,
Hmm.
then the material can no longer have any further strain after the removal of the load, because the force or the stress is a driving force for strain to occur in a way. I mean, there are questions that you'd find, some in the online forums, whether stress comes first or strain comes first. Nothing comes first. Okay, they come together. Or whatever causes what, they happen together. So the thing is, so with no further stress, there is no further unloading and no further regaining of the strain. So at the end of the process of unloading, you have you have some permanent strain. Okay, in a way permanent. Of course, you can reload in compression and make a full hysteresis cycle and come back to zero strain as always. Okay, but then the basic idea is the energy is lost in the process, and that energy would be this much. Okay,
Which is
now,
bound by.
yeah, so now let's not bother about all of this material models, but let's talk about the so-called metal elasticity. Metal elasticity obeys Hooke's law, and therefore it is linear elasticity. Okay, and the uniaxial form basically looks like this. Now we would talk about the multi-axial forms and all, uh, but you need to understand this linear elasticity of metal, that is only valid in this tiny tiny domain of strain. Okay, and so what do we do is, typically in most of the problems that you solved in your undergrad, you try to keep the maximum stress in your system below certain working stress, and that working stress would be yield stress divided by some factor of safety, and depending on the ductility of the material, that would change between 2 to 10. If it is a completely ductile material, then let's say mild steel, or something, then that would be probably 1.5 or 2. Whereas if it is a brittle material, that could be as high as 10 or even higher. Okay, now you see this wave of paranoia in this expression, where we are not designing components up to yield stress. We are defining, uh, we are not going past yield stress by no means. Then we are dividing that into some with a factor of safety to get a working stress, and then even the maximum stress on in our system we want to keep below this value. Okay, and that way, so this is one way of designing components. Okay, that's not the only way that happens, but let's say if we look into this domain where we are desperately trying to keep our stress much below yield stress, there it is okay to assume that metal is more or less linear elastic, which may not be exactly true. For most part of the metal deformation, metal is inelastic, major part. Okay, a ductile metal could be elongating up to 25% or even higher percentage of strain, but it's even 2 or 3 orders below that. The elastic limit is 2 or 3 orders below that, and that is up to which this linear elasticity of yours is valid. But then there is another thing. If you compare the stress values, the stress value which you have over here, and the stress value which you have over here, so this strain may be 100 times higher, but the stress is probably twice or even uh, at best thrice, not more than that. Okay, so if you really compare in terms of the stress values, it seems feasible that you use a linear elasticity approximation for metals for most designing and you know uh, analytical analysis purpose. Okay, again, all of this viscoelasticity, superelasticity, linear elasticity, hyperelasticity, all of these are mathematical models which which are only simplifications of or close approximations of the observed behavior of these individual materials. Okay, metal or material or nature in general is not bound to you know obey the equations or models that you make, apart from few fundamental models. Okay, conservation of momentum, which basically means Newton's laws of gravity. Apart from that, uh, even when situations are not in the hands of relativity or anything else, uh, apart from a few basic equations of physics in engineering, most models are a mathematical equation. Okay, and your material behaves quite different from that in reality, but they can be approximated with those models. Okay, so our model, the only one that you would learn in this course, and actually even that is not warranted, because this course is supposed to be on the mathematical tool that you are learning, not material models. But without the background of any material model, we cannot proceed, or constitutive model, we cannot proceed. So we'll go with linear elasticity, and that is the only one that is supposed to be covered in our curriculum. So we only have linear finite element method. So linearity in finite element method, uh, or rather the non-linearity in any structural problem, appear from three regions. One is material nonlinearity. So what is material nonlinearity? If the constitutive relation is not this, here I'm just talking about the model. Okay, no matter how much strain, if the constitutive material is anything but this one. If you're trying to model elastoplasticity, there are models for that. If you're trying to model hyperelasticity or superelasticity or viscoplasticity or whatever model, any other model, even a model which approximates plasticity like elastic perfectly plastic, that is also a nonlinear material model. Next comes your geometric nonlinearity. Now that we have already discussed what is meant by geometric nonlinearity, purpose of Green's train. If you really think about it, a beam bends on applying load, quite a bit, much more compared to uh, the load would affect in its axial direction. 100 Newton load would affect very little in the axial direction to a beam, but it might have substantial deformation in the lateral direction. Okay. But when we change the 100 Newton load to 200 Newton, we do not consider the amount of deflection that happened or has been continuously happening since 100 Newton to 200 Newton or from 0 to 100 Newton. Okay. We still consider the geometry is flat, and we just apply 200 Newton load, and we assume that the deflection would be twice if we change the load to twice. See, for us, this is PL cubed by 3EI. Okay, and it doesn't change with P. It's just proportional to P. So, so the reason you have such a relation between force and displacement is because of two types of linearity. You considered geometric linearity. That means you didn't consider the change in the shape of the beam, number one. And number two is you considered a linear elastic material, hence the Young's modulus. Okay. With all of these linearity in consideration, okay, you see there is a geometric property over here as well, I, moment of inertia, which could be changing due to lateral compression of the beam. Okay. But we consider the strain to be so small that the lateral compression is even smaller, and then we didn't consider the change in cross section. So when you do not consider any of these, then you have the linear finite element method. The third type of nonlinearity can come from contact. Imagine there is a bar which is free to elongate, and imagine there is a bar which is free to elongate, but then there is a stop in front of it. If it elongates up to certain limit beyond which it cannot elongate, okay, because it comes in contact with the stop, okay, and therefore here it could be showing a force displacement relation which is linear if we neglect the other two non-linearities, but here it would be something like this. If I imagine there is a rigid stop, then you need infinite amount of force to cause any further deflection. Does this make sense to you?
Yes, sir. This last makes sense. Because if we reach the end, then
Yeah.
in
So
however
the
order
point
we
is,
increase the force, it will not
so
increase.
point is that with contact also the system behavior changes. By system behavior, I am strictly talking about the stiffness of the system, the instantaneous stiffness of the system. If that stiffness is going to be constant throughout, then it's a linear finite element method problem, which is the tiniest domain of the finite element method, but the most basic version of it as well. And if you expect the stiffness to change from a finite value to an infinite value, or to decrease or to become zero, anything, okay, so that would be non-linearity. Okay. Now we are not considering any form of non-linearity. We are simply going for linear elasticity and geometric linearity and no contact. Okay. So at this point, let's consider what could what is the the multi-axial formulation for linear elasticity. Now, not only are we considering linear elasticity, but we are also considering isotropy. Linear, elastic, and isotropy. What does the last term mean? Last term means that if you pull that in x direction and to cause, let's say, uh, epsilon amount of strain, you need sigma amount of stress. And then you pull it on y direction with the same amount of stress, and if you get the same amount of strain, then the material stiffness in any direction is the same. So there are two things you need to be able to distinguish. One is homogeneity. That means the material is the same from end to end. Okay. everywhere in within the volume, the material is the same material properties, density, Young's modulus, everything. And the second thing is which comes into play when you have tensorial properties. That means the Young's modulus has many different components. So the point is, I mean, not components. That means these are direction dependent, but in all direction, if the Young's modulus is the same or any other property is the same, okay, then that material is called isotropy. I mean, when I'm talking about any other property, it cannot be density, okay, because density is a scalar property, okay, whereas Young's modulus is a part of tensorial property, okay, which is the elasticity tensor. So Young's modulus is one of the components of the elasticity tensor. We would see how. Now, in linear elasticity with isotropy, this is how you can represent the general relationship between stress and strain. And this representation is necessary and sufficient. I'm not going to prove the necessary part of it. Of course, there is a proof in any continuum mechanics book, but I'm going to show you that this is sufficient, that this makes the material linear, elastic, and isotropic. To check whether it is linear, let's try. So let's call it a function sigma hat of epsilon. Now try sigma hat of alpha times epsilon 1 plus beta times epsilon 2. Now at this point, sigma hat is just a tensorial function of a tensor quantity. Tensor quantity, which is strain, and its tensorial function is the sigma hat. Gives you the stress. Okay. And at this point, these are some random 3 by 3 matrices. Okay. Symmetric, of course.
Yes, sir.
Okay. So I can show you that this is going to be lambda times trace of alpha epsilon 1 plus beta epsilon 2 times I plus twice mu alpha epsilon 1 plus beta epsilon 2. But then after that, I can show you that trace of two matrices is essentially the trace of sum of two matrices is essentially the sum of the traces. As simple as that. Basically, you are adding the diagonal terms up. So in that way, you can write it to be lambda times trace of alpha times epsilon 1 plus beta times trace of beta times epsilon 2. But then if you think about it, if you do a scalar multiplication to all the components, the trace simply gets multiplied by that quantity. So it is trace of alpha times trace of epsilon 1 plus beta times trace of epsilon 2. This whole thing times identity tensor plus alpha times twice mu epsilon 1, because at this point these are simply scalars. Okay. And in the end, I can write this is to be lambda alpha times lambda trace of epsilon 1 times I plus twice mu epsilon 1 plus beta times. So essentially, this is sigma hat of epsilon 1 plus beta times sigma hat of epsilon 2. I can write. So when you can write a functional form like this, that is, if f of alpha x plus beta y is essentially alpha times f of x plus beta times f of y, that is the ultimate proof of linearity. Okay, here we can do that. Hence, this relationship is linear. Now, anytime a constitutive relation is linear, it is also elastic. Okay. Why? Think about it. If the constitutive relationship is this, just given by a single line, here I am taking the uniaxial example. So for a given value of strain, you will just have a single value of stress, unlike in plasticity. Okay, sorry, not this one. Unlike in plasticity, because you do not know whether you are loading or unloading, or from which point are you unloading. Depending on that, you can have multiple values of stress for a given strain. Okay. But if it is said that the constitutive relation is just a single line, and it doesn't matter whether you are loading or unloading or doing anything. Okay. So even with a nonlinear relationship, if it's just a single line, it has to be elastic, like hyperelasticity. Now, if it is a line, okay, straight line, and that is the only relationship that is there between stress and strain, and any moment you know the strain value, you know the stress value, and you do not need to know what has already happened to the material, whether material has been previously loaded and unloaded, now it is being unloaded, or now maybe it is being even reloaded. You don't have to know anything about it. Okay. So the point is, in that situation, the loading and the unloading curve are same, because you do not need that information when you write this expression over here. It's a linear relationship between stress and strain. So inevitably, this relationship is also elastic. Is this part clear?
Yes, so this part is clear.
Okay. The third thing is isotropy, and let me try this. This is how you rotate a strain tensor. Earlier, you were applying certain strain in x direction and certain strain in y direction. Now you have rotated it, that now the strains are acting in 90-degree rotated. So the strain in x direction is now acting in y direction, and strain in y direction is now acting in x direction. So these q's are arbitrary. For any amount of rotation, what we are about to write is going to be true, which is lambda times trace of q epsilon q transpose times I plus twice mu q epsilon q transpose. Now think about it. Trace is an invariant and it doesn't change if the matrix is rotated. Also, we know that trace of AB is a trace of BA, which basically means trace of Q epsilon Q transpose is a trace of epsilon Q transpose Q, but then Q transpose Q is an identity tensor. So this right here is trace of epsilon. Also, I can write this I matrix as Q times Q transpose. So I can write lambda times trace of epsilon times Q transpose, or Q times IQ transpose. Because Q times Q transpose is an identity matrix. So Q is a orth plus or rotation tensor. So twice mu Q epsilon Q transpose right here. So now I can do this Q over here and Q transpose over here. And within bracket, square brackets, I have lambda times trace of epsilon times I plus twice mu epsilon, which is but sigma hat of epsilon. So now it shows that if you rotate the strain, that means, let's say earlier the strain was 0.001 and YY was 0.0005, and now you have rotated uh, this into 0.0005 and this one as 0.001, so basically rotated by 90-degree. So the stress also simply gets rotated. So you take this to get the strain for a rotated strain tensor, you get the stress for the current strain tensor and rotate it. And this is what is isotropy. মানে আগে তুমি x ডিরেকশনে বেশি স্ট্রেন দিচ্ছিল, y ডিরেকশনে কম। ওকে, and so you would have higher stress in x direction and lower stress in y direction. Now you have, reversed the situation, and the stress also simply gets reversed in the
Level.
proportionally. Okay,
Yeah.
to put it in a single sentence, you want to get the stress for a rotated strain tensor. You get the strain tensor for the current uh, stress tensor for the current strain, and then rotate that with the same set of orthogonal tensors. Okay, that is what is meant by isotropy. This is actually the very definition of isotropy. Okay, so the constitutive relation that we just wrote, these parameters are called La May parameters with lambda and mu. And this constitutive relation, as we showed, is sufficient to demonstrate linear elasticity with isotropy. It also happens to be necessary, but I'm not going to show you that proof. Okay, so now we have the constitutive relation. So this could also be written like okay. So trace of epsilon, or epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3, is regarded as a volumetric strain. Okay, and this part is known as the deviatoric part of the strain, this tensor right here. What is the deviatoric part? If you take the trace of the deviatoric part, it would be trace of epsilon minus trace of epsilon divided by 3 times trace of identity tensor. Now, what is the trace of identity tensor?
It's free.
It's 3. So essentially, once you multiply trace of epsilon divided by 3, or epsilon v divided by 3, to each component of the identity tensor, and then you take the trace of it, so you essentially get the trace of the strain tensor. So this is actually 3. So this happens to be 0. So now I have transformed the strain tensor into deviatoric strain tensor, whose so basically this represents no amount of volumetric strain, but other type of strains, mostly shear strains. Now, this type of a relation can also be shown with stress tensor, where it is minus p times I plus s, where minus p is bulk modulus, minus p is essentially bulk modulus times epsilon v. So from this relationship you would get that k happens to be lambda plus twice mu by 3, and and s simply happens to be, so what is s? S is essentially sigma minus trace of sigma divided by 3 times I. Okay. Achha, by the way, the volumetric part and the deviatoric part are mutually exclusive. It's like uh, taking a vector, taking a vector and taking its normal component and tangential component. Okay, so one component which is normal to a given plane and the other component is tangential to that plane. So essentially, the deviatoric stress tensor is essentially like the shear component, and the
Yes, sir.
hydrostatic part is essentially the like the normal component. Okay,
Yes, sir.
okay. So they are mutually exclusive. Basically means they are orthogonal to one another.
Yes.
Which basically means if you take this tensor and if you take epsilon d and do a matrix inner product, so essentially if you do, see, this part is all scalar, right? So the only matrix over here is the identity tensor.
I did it.
So if you do an inner product over here, so basically this means that take the individual terms of identity matrix and take the corresponding terms of epsilon d, multiply them and add them up. But now you know that in identity tensor, the only three terms that are non-zero are the diagonal terms. So basically,
Done.
this would mean epsilon 1 1, epsilon d 1 1 plus epsilon d 2 2, epsilon
Two,
d
three.
3 3. And you know that this would be trace of epsilon d, and trace of epsilon d happens to be 0. Since this matrix inner product is 0, they are mutually orthogonal uh, matrices. My point being that this representation is unique. Okay, so if the stress can have, two different ways of representation, so the individual components, the hydrostatic and the volumetric part for stress, sorry, hydrostatic and the deviatoric part, so this is the deviatoric stress, and for stress we call this portion as the hydrostatic part. For strain it is volumetric, for stress this is hydrostatic, and this p right here is the hydrostatic pressure.
Yes, sir.
So this S, as you can see, is twice mu times epsilon t. Now, if you think about it, the only thing that changes between epsilon and epsilon t are the diagonal components. That is the normal strain components. The shear strain components are same between. Basically, all I'm trying to say here is this is epsilon d xy. Also, S xy is S xy is same as sigma xy. Now, now we know, and this is true for any shear component, sigma xy is g times gamma xy, gamma g being the shear modulus and gamma being the shear strain. Now, gamma is twice epsilon xy. Okay, and since S xy is also this quantity, and this thing is also epsilon d xy, so that only goes to show you that G is essentially mu. Okay, so this is the relationship between shear modulus and mu, and this is the relationship between bulk modulus and the Lame parameters. Okay, but then you also know G equals E divided by twice 1 plus nu, and K is E divided by thrice 1 minus twice nu. Okay, so from this, I need you to express. So this is your assignment 1. I need you to express Lame parameters as functions of Young's modulus and Poisson's ratio. Okay.
Okay, sir.
Okay. Acha. Now if I represent stress in Voigt notation, it is 6 components, which equals strain represented in Voigt notation, which is epsilon xx, epsilon yy, epsilon zz, gamma xy, gamma yz, gamma zx. Now I would need you to go back to the earlier representation of sigma equals lambda times trace of epsilon times I plus twice mu epsilon. So in this, if you write sigma 1 1 or sigma x6, that would be lambda times epsilon x6 plus epsilon yy plus epsilon zz plus twice mu epsilon x6. Okay. No shear strain terms are involved. So now I can write this to be lambda, 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 0, 0, 0. That is this portion. But then I have twice mu over here. And if you repeat the operation, this is what you get. Okay. When it comes to shear stresses and strains, that is simply, you see the off diagonal terms of the identity matrix is 0. So this basically means this quantity or mu times gamma xy. So 0, 0, 0, 0, 0, 0, 0, 0, 0, mu, mu, and mu. Okay. So this is how you populate the. So this one right here is the strain tensor in Voigt notation. And this is your 6 by 6 elasticity tensor, which should have been, see, ideally this is an 81 component elasticity tensor, fourth order. But then, using the symmetry of the stress and the strain tensor, you can reduce it to a 6 by 6 second order elasticity tensor. So once you have gotten the expression for Lame parameters in terms of Young's modulus and Poisson's ratio, I need you to substitute them in this matrix and have the relationship between the stress and the strain components.
Okay, sir. That is the second
Okay,
assignment.
that is, yes, that is your second assignment. So get the full 3D elasticity tensor. Okay, and I don't think today we'll be able to cover variation formulation. We are already out of time, so we'll stop here. We have already covered at least the constitutive relation.
Yes, sir.
তো বুধবার যদি আসো তাহলে
हाँ
সেই
हाँ
পার্টটা ডিসকাস হবে, না যদি আসো
ओके सर
তোমাদের ব্যাপার। So at this point I'll just stop the recording and also stop the presentation, but if you have any other queries you can ask them.
no, up until now it is absolutely clear.